Hello and welcome everybody to our new seminar within Commission J1 of the IAU. So today we have Camilla Pacifici from the Space Telescope Science Institute in Baltimore in the United States. Camilla did her PhD in 2012 at the Université de Sorbonne in Paris, in France, under the supervision of Stéphane Charlot at the Institute of Astrophysics of Paris. And then she went on to work on several postdocs at the Max Planck Institute in Heidelberg, Yonsei University in South Korea, Goddard and the Space Telescope Science Institute, having different positions, among others, for instance, working for the Canadian Space Agency for one of the instruments on James Webb, for NIRISS. At present, she actually has the position of a senior astronomer data scientist for the James Webb Space Telescope. And it's fantastic to have her give this talk on the art of measuring galaxy physical properties. Thank you. Go ahead, please.
Okay, thank you very much. Let me get ready sharing the screen. Okay, I have a giant mouse now.
Perfect. Yeah.
It should do it. Okay. Okay, thank you so much for this opportunity. I think it comes at a very nice time because I don't have science time anymore, but I just happened to get a paper out at the beginning of this year about really measuring galaxy physical parameters, and I'll tell you during most of this talk, I'll tell you about that. I'm a data scientist now. You can find my email on this screen and also my Twitter handle if you want to follow me or figure out what things that happen. Also, STScI, I tend to retweet things that happen here. It's okay. The art of measuring, heart also probably a good way of describing it, of measuring galaxy physical properties. So the outline of the talk goes through my favorite science topic, which is to understand how galaxies form and evolve. And then the art of measuring and the art of modeling galaxy SEDs to be able to interpret the data and get out physical parameters from the data. The philosophical question of why we need complicated models of galaxy SEDs, I'll address that too. And then I'll show you a couple of examples of things we did in the past years or the most recent this year. What we did with star formation history reconstruction. So out of deriving physical properties for galaxies, my favorite part is really deriving star formation histories. So we can do powerful things, deriving star formation histories from data. So how do galaxies form and evolve? So we see many different types of galaxies in the universe. We see beautiful spiral galaxies with active knots of star formation, clumps, and we see the stars are forming. We see galaxies in the process of getting to quiescence with some more red zones, whether that's old star populations or whether it's dust obscuring. We need to figure that out by interpreting the data. And then we see nice spheroidal things that I like to call red potatoes, which are red and dead galaxies, essentially. So how is this transition happening? And there have been studies from like the past 30, even 40 years, even maybe more about this. And in all of these, we see bimodalities in galaxy properties. So we know that there are two separate populations, and the bimodalities can be in color, in activity, in morphology. So there must be something happening between these two populations and something moving between these two populations. And the basic possible scenarios are two. Is that the most basic, that a galaxy forms in with blue colors and stays in blue colors for a little bit of its life and then dies, transitions to the red sequence in a color stellar mass diagram like I'm showing here, and then spends the rest of its life like growing, but from just accreting stars, but not doing more new star formation. Another potential option is that a galaxy stays in its active phase for the majority of its life and then transition when we observe it. So at the end of its life, when we can see it. So grows by active star formation. But I want to argue that there can be other options. A galaxy can go up and down between these two and start forming stars, then stop forming stars, then more gas comes in. So and it goes back to the blue cloud, and then again it's exhausting the gas, or there is a merger, something happens, and there's no star formation again for some time, and then so it goes up and down between these two populations. And I believe that this is from what we see. From the observations also at higher redshift that we're seeing now, I think this is a better representation of what can happen in a galaxy. So everything can happen, whether it's for mergers, gas inflows, or other environmental massive events. A galaxy can go through a lot during its life. So we see changes. We see changes in morphology, in kinematics, in star formation activity. And we know a good deal here because we have simulations and we have these observations of changes. And so we know that the mechanisms that can cause these variations from one type of galaxy to another, or one star formation activity to another, can be mass accretion, can be feedback, can be gas consumption, can be because of the formation and destruction of dust, can be because of outflows. So we know a good deal about these mechanisms, but I think we don't have the final version yet. Some redshift, we still cannot explain everything, and this is a good thing. We still keep our jobs trying to figure out what happens in the universe. So there are two ways in which people tend to answer these questions about how galaxies form and evolve. One approach is to connect galaxies observed at different epochs and infer how they evolve globally, so as populations of galaxies. Another way is to interpret the light of galaxies and infer their individual formation histories from the fossil records in the data. And this is where the star formation histories come into play. These two approaches are equally valid. They have their pros and cons, and they give answers to different science questions. So they're both very, very valid. What I'll show you in the next few slides is a perspective on how to understand when you need one and when you need the other approach. So for example, we can connect galaxies observed at different epochs and infer how they evolve globally. And this is very much like looking at pictures of people. So we can look at the picture of a person, and we can learn a lot about their properties, their characteristics, their environment by looking at this picture. So it's very much like looking at a picture of a galaxy. And in this case, I'm looking at the 1920s, and I'm making the case that it's like looking at a galaxy at high redshift. And then we can look in the 50s and see other properties, different environments, different things happening to these people or these galaxies. Same thing, we're looking at the picture from the 70s, completely different story. Or we can look at the picture from the 2000s. And if I look at these four women, they have absolutely nothing to do with each other. They don't have a connection. They all represent a certain population. They all represent a certain epoch. But I could also argue that the late Queen of England is not very representative of the people in their 90s in Europe, right? So it really depends. Connecting populations of galaxies, we need to be very careful in selecting the samples that we're trying to connect. But it's simpler because we have a lot of statistics for each individual epoch. If instead we try to interpret the light of galaxies and infer the individual formation histories from the fossil records, we don't have this problem of connecting galaxies that don't have anything to do with each other. But it's harder because we need to extract the information from the view of the galaxy we have at observation. Although with the amount of data we have now, I will argue through this talk that we can do that. So we can, with the amount of data and the quality of data we have now, we can tell how many old stars are there, how many young stars are there, whether there is active star formation, whether there is hidden star formation because there is dust. So there are a lot of information that we can gather from the information in the data, from the fossil record in the data of individual galaxies. And this is just an example of a galaxy. This is a local galaxy, it's an STSs galaxy. And we can look at it at different wavelength and extract different information from every individual picture here. So for example, if we look at in the ultraviolet, we see the youngest stars. We see the stars that are forming right now when we observe it. And this is the purple image here. Then we can look at the near infrared, and again, we still see young stars. If we go through the optical, we see slightly older stars. Then we can put on a filter that is on the H-alpha line and the hydrogen line, and there we see again the knots of star formations and kind of going in couples with the UV image. And then we go to the near IR and we see the bulk of the older stars, and you see it's brightest in the center where the older stars live. And then we go look in the IR and we see the complementary image compared to the near infrared, because all the light that the near UV, because all the light that gets absorbed in the UV gets re-emitted in the infrared. And so if we can look at all the wavelengths, we can get the information from every component of a galaxy and combine it to measure the formation histories from the records in the data. So this is where modeling galaxy SEDs come into play. So how do we model galaxy SEDs? First of all, we need to build a library of spectra. Now, there are, just to go into a little bit more of a technical detail, there are two types of codes essentially to do SED fitting. The codes that build the library beforehand, and then they run the analysis using this library, and the ones that build the library on the fly while it's created. So now I write build library of galaxy spectra, but it applies to both cases. It's just that in one side it gets created during the fact, and in the other case it gets created before. So what are the ingredients that go into this? We need star formation and chemical enrichment histories. We need the emission. We need to model the emission by the stars, the emission by the gas, and the effect of dust. And I say the effect of the dust because the dust comes in both absorption and emission characteristics. So we need to model both depending on what data we're analyzing. And then we use these models as priors to interpret the observation. So we need to try to be as physically motivated as possible. Okay, so first ingredient, star formation and chemical enrichment histories. And this is something that can be done in many different ways. Long time ago, people tend to use star formation histories that were exponentially declining tau models. So something that jumps up when the galaxy is formed and then has a long declining tail, long or short declining tail. And that was perfectly fine when looking at galaxies at local massive galaxies. Local massive galaxies respond very well to that type of star formation history. They form that way. But now that we have more data, more high redshift data, we need to go into a bit more details in how we model the star formation histories of galaxies. So here I'm proposing 3 examples. One is the parametric. The exponentially declining is a parametric function, but it's not very flexible. It just has one parameter, and everything jumps up at the very beginning of the universe, and then there's a tail. There's not a lot of freedom there. So a very good way to measure, to generate parametric star formation histories is to use double power laws. So functions that have a rising, reach a peak, and then decline, and have quite a lot of freedom in how fast they rise, how fast they decline, and when the peak is happening. And this is an example work, an example figure by one of Adam Carnell's paper, where the authors show how the combination of many double power laws can create an SCD, the orange one, that doesn't look like even an analytic function, but in the end it was generated by analytic functions. Another option is to use non-parametric star formation histories. These are basically bins in time, and the fit fills these bins with or without that the bins talk to each other. So there can be a continuity prior so that they can follow some kind of shape, or there can be the what we call the ignorant prior, where the bins don't talk to each other, and so you can fill the bins as the fit will fill the bins as it prefers, essentially. And this gives a lot of freedom in the shape of the star formation history. You can see that this star formation history is quite bumpy, and it has a rejuvenation event at observation, which is not possible to model with an analytic function that is a double power law even, for example, because it's just one power law, so it cannot have a rejuvenation event at the end. The drawback of this is that it's very sensitive to the width of the bins, so the tests need to be carried out while doing the fit to figure out what's the best size of the bins. Another approach, which is the one I tend to use, is to base the star formation histories on simulations, which means go to a simulation, whether it's an hydrodynamical simulation or a semi-analytical model. I used to use semi-analytical models for this. Get out star formation histories from there and use those. So those are definitely not analytic function. They're not the non-parametric kind where you can fill the bins as you want, but they're driven by physics. And so that's a very good prior to have, a prior driven by physics. The other pro is that usually using simulations, the metallicity history comes for free, which is very important because we know from observations that the first stars should be metal poor and the last stars should be metal rich. So this is a metal enrichment history, so metallicity on the y-axis and look-back time on the x-axis, and you see that the metallicity is growing throughout the life of these simulated galaxy. This is a star formation history from a simulation. Bursts come for free in some sense. They're driven by physics as well. The drawback of using these is that, just like the non-parametric, it requires a lot of tests because simulations are built to match some observed samples. But in that case, the specific simulation will be good to fit that specific sample. If we want to fit a sample that has different characteristics, we need to play with the simulated star formation histories and make sure that the colors that we derive from the simulated star formation histories can reproduce the colors of the galaxies that we want to fit, so the galaxies that we observe. So more complex star formation histories require more tests.
Put on Cammy's talk. You don't need to call in. It would overrule your brain right now.
Sorry, I'm hearing somebody. Okay.
Yeah, please go ahead, Camilla. Yeah.
Okay,
Sorry
thank you.
that.
No problem. I thought it was a question. Okay, so more complex star formation histories require more complex checks, but they also are more powerful than very simple star formation histories. This is an example work by Triani et al. In 2020, where they built star formation histories from a semi-analytical model, including dust formation and distraction, which is not very common to find among the semi-analytical models and simulations. So this is a very powerful set star formation histories that can be used to generate SEDs to then do SED fitting. So that was the first ingredient, then the emission by the stars and emission by the gas. The emission by the gas gives the emission by the gas is the emission lines that we see in the spectra. And the emission lines can be strong or can be not as strong. We know from diagnostic diagrams like the BPT diagrams and the various versions of these ratios of lines that they follow specific trends in these plots. And we can model these using photoionization models. And that's the way I used to do it, but people can also use just ratios of lines to add the emission lines to the spectra of the stars. And it's very important because even when fitting the photometry alone, the emission lines can contaminate the broad bands. And this is a plot of the contamination in one of the Hubble bands in F140 as a function of stellar mass. This was done with the 3D HST survey. And this shows how much an excess of flux in a band is due to the emission lines that fall in that band. And it's not just more stars. So we need to account for that. I'm plotting here the 5% uncertainty level, which is the usual uncertainty for photometry. So whatever is in excess there would be interpreted as signal. And if the emission lines are not included in the model's SED to interpret the data, that excess would be interpreted as more stars, wrongly interpreted as more stars instead of as gas. So recent star formation. The last is the effect of dust. Dust can be modeled. I mean, there are multiple models of how dust affects the SED of galaxies. A powerful model is the two-component model, where the stars that young stars are still embedded into their birth clouds. And so the light emitted by these young stars is first attenuated by the thick birth clouds, and then it's attenuated by the thin ISM, which is this path. While if we look at stars that are have already blown away their birth clouds, their light is attenuated only by the thin ISM. So depending on the age of the stars, the attenuation is different. And we see that that's important to look at, and we see it from work by Wei-Chen Wang in 2018, for example, is one of the works that looked at galaxies age-on and face-on in the IRX-beta relation. So the IRX is the excess flux between the UV and the IR, and beta is the UV slope. So if we were to use the slope of the UV as the only measure for dust, we would interpret different populations of galaxies as having more or less dust, while instead they don't have more or less dust. We're just looking at them with different orientation. When we look at them edge-on, we see essentially the ISM. We don't see the knots of star formation. So we see thin dust, a lot of thin dust. If we look at the galaxy face-on, then we see all the knots of star formation. But not too much dust, because the is thick but not too much dust. So it's a steeper dust law with less dust. So it's more complex than just thinking of a screen, and that's the whole message. So it's important to account for dust laws that it's important to use dust laws that account for the fact that the dust can be shielding stars in different ways. Okay. It's all about the priors at the end of the day, because we need to create priors that match the observations we are about to observe. So, for example, if we have this is just a cartoon, we have flux versus wavelength, and we have data. Then we build a prior that in a certain parameter, whatever that is, it's shaped this way. If we use this prior to interpret the data here, the answer can only be in this range of the prior. That's the whole point of a prior. If the prior was distributed in a different way, maybe we would find something like this. So the favorite answer is somewhere at a higher value of that parameter. And there is a little bit of an answer here. But we were missing this result by using a prior that was too restrictive. So it's all about the priors. And why should we build such complicated models of galaxies as CD is exactly because it's all about the priors. And we need to match what we see. And many years ago, the observations of local massive galaxies with a few photometric measurements, suggested that galaxies were very old objects with a tail of star formation. So that approach, with simple modeling approach, was perfectly fine. But now we have observations of local and high redshift galaxies. We have photometry in broad and narrow bands. We have large wavelength ranges, spectroscopic measurements, high resolution, high signal to noise ratio. So a simple modeling approach is not enough anymore. It is important to account for the details in the data. There is such thing as too good data. The more the details in the data, the more the details needed in the modeling. So my ask to you is, please don't use SED fitting tools blindly. Check that things are working for what you actually need. This is an example of why people should not use SED fitting tools blindly. It's a bit of a complex plot. I'll explain it little by little, so just stay with me. Plot on the left-hand side is mass function. So number of galaxies as a function of mass. The dotted lines are observed mass functions at redshift 1, 1.2, 1.6, and 2.2. And you see the shape, totally acceptable. We know the mass function is done like this, more low mass stars than high mass stars. If we use star formation histories from cosmological simulations or in any way complex star formation histories, we can take the galaxies observed at redshift 1 and trace them back in time and build the mass function based on these observations at redshift 1. And these are the solid lines. And they work pretty nicely. They match what we actually observe at higher redshift. So this is a good case for the need to use star formation histories that are more complex than just a simple tail. In the other plot is still a mass function. This is generated using simple exponentially declining models. You can see that the dotted lines are still okay. So masses derived with very simple star formation histories are still fine. But if we do the same exercise and run back in time the star formation histories that we derive at redshift 1 from these blue points, we don't match anymore. So the masses might be all right, but all the rest is wrong. And especially the ages are wrong. So if you just want to derive masses, I would say, okay, you can use something very simple. But if you want to do something more than just masses, then it's important to use models that are more complex than just that. And so, and this is where I start talking about the paper that was published early this year. This came from an almost a sociological experiment. In 2018, we put together 13 or 14 SED fitters in the same room. We gave them the same data set and we said, fit it with your best possible assumptions, and then give me back your results. And so I spent more than a year after that meeting we had, making sense of all the results, making sure that there were no bugs, no strong biases, no problems. So after a year and a half, I was ready with the results, and then pandemic and everything else that happened. So that's why it got delayed so long. But after 4 years, the paper was out. I'm not expecting that you read this table, but since this talk is recorded, if people are listening to it afterwards, maybe they want to just stop and read it. So I included just for that. It's the same table that's in the paper, so you can also go that and check it. But this is the list of exactly what code we used, what sampler they were using, so whether they used MCMC or a grid or an atlas to build the library of galaxy SEDs to do the SED fitting, what type of star formation histories they were using, what type of stars, whether there was nebular emission, what dust attenuation, what dust emission, and whether they were including AGN. So this is the information you don't have to read now. I just want to make sure you know that this table exists. So what were the samples of galaxies? We gave 2 samples to the SED fitters, about 300 galaxies at redshift 1 and about 100 galaxies at redshift 3. These were samples were both extracted from Candle's photometry in the good south field, and were very vetted photometry, like really nice objects, no peculiar thing, no strange things. The photometry, these are to model SEDs, one at redshift 1 and one at redshift 3, to show you that the filters we used from the U-band to IRAC channel 2 were covering the UV to the near IR in both cases. More UV in the case of redshift 3 and less IR, but still, and less near IR, but still UV to the near IR. So these are example fits. We have an image of a galaxy on the left, and then plots of star formation rate versus stellar mass, AV versus stellar mass, and AV versus star formation rate. These were the 3 parameters, stellar mass, star formation rate, and AV, that I asked the fitters to give me. And so this nice spiral galaxy, you can see that there is consensus both on star formation rate and stellar mass. The yellow line on the plot shows the location of the expected star formation rate stellar mass relation, or called also main sequence, at redshift 1. This is part of the redshift 1 sample. You can see that although there is consensus on star formation rate, there is a little bit of a spread in AV. And you can see it also in the last plot. So star formation rate versus AV, you see a little bit of a spread in AV. The second example here is a quiescent galaxy. All codes say that this galaxy is quiescent, which is very good news. Again, there is a spread in AV, but they all agree on the mass, and they all agree on the fact that there is very little star formation. This is a more problematic case, I would say. This is an example of where things don't go as well. Although the mass is still in good agreement between all the codes, the star formation rate starts to have a spread. And with a spread in star formation rate comes a larger spread also in AV. And here we can see very clearly the dust star formation rate degeneracy. So for the codes that say the star formation rate is low, also the dust amount is low. For the codes that say the star formation rate is high, also the dust is high. So a red SED is interpreted as a lot of star formation rate and a lot of dust, or little star formation rate and little dust, more old stars. So these are basically the 2 options. Now the scary part. So I plotted the star formation rate stellar mass relation for all the individual codes. You will see this is not pretty because they're all different. And if I were to interpret each one of these at face value, I would conclude different things on the feedback mechanisms for these galaxies, on their star formation histories. I would conclude different things from each of these codes. The thing that is missing if I do that is the uncertainty on the modeling and the uncertainties, the additional uncertainties on this parameter due to the modeling uncertainties. And this was the result of this study. So basically, not all is lost, because if we combine the informations from all the codes and we plot the median star formation rate versus the median stellar mass, where the median is the median of the distribution of all the stellar masses for each galaxy from the 14 codes, 13, 14, this is a very, very reasonable star formation. This is a very, very reasonable stellar mass star formation rate diagram with very, very reasonable value for dust. So what do we have to estimate to be able to take the measurement from an individual code and compare it or derive final answers for the physics of galaxies. We need to account for the modeling uncertainties. So what I'm plotting here is the dispersion. For every galaxy, every point in this plot is a galaxy. For every galaxy, I have a distribution of values from the individual codes. So each code gave me a number. So with these numbers, I can create a distribution. And so I can get a median out, which is what we saw in the previous plot, and a dispersion. So this is the dispersion. This is that value as a function of stellar mass. And you can see that it's fortunately not a function of stellar mass. It's pretty flat, and it's around 1.1 dex. So if we were to get the measurements from an individual code, we would have to add in quadrature a 0.1 dex uncertainty for the mass. The story in star formation rate is a little bit different. For galaxies that are star forming, this dispersion is a little bit large, but it's the same for all the galaxies that are star forming, or the majority of the galaxies that are star forming. Outliers are always there, but it's around 0.3 dex. So it's a little bit large. And if we look at galaxies that are not star forming currently, this dispersion explodes. And the reason for that is that it's really, really hard to tell the difference between a star formation rate of 0.002 and a star formation rate of 0.0002. So it's 1 dex in log, but it's very little in real units. So it's basically, okay, there is no star formation. So that's why we see it exploding here. But still 0.3 dex for the star forming galaxies is a little large. And for dust, it's another different story. It's around 0.3 magnitude, but it's a strong function of AV itself. So galaxies that are more attenuated by dust also have the largest dispersion or largest modeling uncertainty for the AV parameter. So what we tried was to include Far-IR measurements to see if we can pinpoint the dust better and see what we can learn from measurements without the Far-IR. So for a smaller sample of the galaxies, it's about 100 galaxies, we had measurements at 24 micron. Some had measurements at 50 micron, and a few had measurements out to 250 micron. And so we compare the results for the individual galaxies with the IR, with the median that I showed you before without the IR, so that the baseline is the same for all the codes. It's not dependent on the code itself. And we see that in general, we see more points below that black line, which means that the codes were, without the IR, the codes were we're assuming that there was more dust than what there really was. So they were adding more dust, and so adding more star formation with it. If we include the IR, the feed now knows that there is not that much dust, and the number for AV decreased, and so the star formation rate also decreased. So that's something we learned. But we also learned that for the codes that had complex star formation histories, or star formation histories that had some kind of rising part at the beginning and could add more old stars, this effect was mitigated. So with and without the IR, there wasn't that much, there wasn't as large of a difference as for the codes that did not have that freedom of adding more old stars to the SED. The other thing we checked was about the AGN component, because there are some codes that can fit with an AGN component as well. So we saw that for the majority of the galaxy, the AGN fraction was very little. Just the fact of including a component take lights away from other things. So some of the light was just automatically interpreted as AGN. So it's not like they're all at 0 and we see only a few AGN. There are like the baseline is like 5%, 10%. 5 or 10% of the light was always given to an AGN. But the orange points are the ones that are actually identified as AGN with color diagram in the mid-IR. And all the codes return larger fractions for these orange points, at least 3 out of these 5 orange points. So in the case when the AGN was actually there, they were doing a good job giving the light to the AGN instead of to the star formation. But the AGN has to be really strong for that to happen. So this is a flowchart that is in the paper as well, and it shows what to do a CD fitting. So first of all, you need to get to know your data set. And when you get to know your data set, then you find out what's the suitable fitting tool for that data set. Sometimes you don't need a data set that goes out to the radio if you don't need a fitting tool that goes out to the radio if you're only fitting UV and optical. These kind of questions, the wavelength range, the resolution, whether there is a very specific selections. You're only looking at very low metallicity galaxies. You don't have to include in your sample, in your library of model SCDs, a lot of high metallicity galaxies, right? So then you define the appropriate priors, star formation history, metallicity, nebular emission, and all that. And then you have to check that. Check that the priors are actually appropriate. So do the models reproduce the range of the observables? And you can very well say no to that. And then you go back and you redefine the priors. Or when you get to no combination of priors work, I don't have a model for these specific galaxies, you can try a different tool. Or you can challenge the modelers to improve their models, because clearly there is an observation that is not represented by anything. Or you can just say, I did not check, but I'll take my chances and keep going. That's also an acceptable answer, I would say. You keep going, and then you run the SCD fitting tool, and you extract the probability functions for the parameters of interest. And then you have to assess the quality of the fit. Sometimes the results might hit the edge of the prior. And then you have to go back and redefine your priors, because that answer might be biased by the choice of priors. Or the probability distributions might have the exact same shape as the prior. And that tells you that the data don't have the information you're looking for. For example, an example of that is you're fitting the photometry alone and you want to extract the ionization parameter for the emission lines. That's not going to happen unless you have objects with super strong emission lines, and even then it's very hard. So it's fair to get the results out and say, okay, the information was not there, I cannot constrain this parameter. It is totally fair. Okay, so every data set has its own challenges, so that's why we need to think a lot when building these libraries of stellar populations and nebular emission, dust, when we interpret the observations. And so, for example, in the past few months, we have seen JWST breaking all these assumptions. And like we've seen excess of mass that could break the cold dark matter paradigm. We have seen excess of dust that cannot be explained by by the enrichment mechanisms we know. We have seen no dust at all. Would need very strong winds to clear all the dust from some of these objects. We have seen objects with very strong emission lines that could be from population 2 and population 3 stars. We have seen no lines at all at very high redshift. How can that thing be quiescent? We've seen so many weird things with JWST now, and I'm 50% nicely puzzled. We are learning new things. And 50% we need to dig more in the way we interpret the data. So there are these two things to keep in mind. Not all these excess results are worrisome. So if I haven't convinced you yet, why really should I care? And why do I have to measure, do these fancy measurements? And the reason is that because we can do more than just measuring masses. And we can do more than just measuring masses and star formation rates. We can measure dust, we can measure star formation histories. And this is my favorite thing, measure the star formation histories of galaxies. And I've done it in many different ways in the past, but the last two, the results that I want to show you today are two specific results. At redshift 1, we use the spectroscopy and the photometry, but with a disconnected approach, to measure the dust laws in galaxies. And another thing is more recent with JWST data, we measure the star formation histories of the little knots that we were seeing surrounding a galaxy at redshift 1.3. So star formation history reconstruction. The dust attenuation work, it was led by Ivana Barizic back in 2020. So basically we took these very, these high resolution, very, very high signal to noise spectra, redshift between 0.8 and 1 from the legacy survey. We wanted to use the photometry and the spectroscopy, but they're disconnected. So the first thing we did was to continuum subtract the spectra so that the photometric information, which is the shape of the spectrum, was not included in the fit. So continuum subtracted, now the fit is flat, the spectrum is flat, and we only have access to the features of the spectrum. So all the absorption features and the emission features in the spectrum. So we fit the spectrum as it was that way and extracted star formation histories. And the information is there because the star formation histories is encoded in these absorption features in the G band, and the most recent star formation history is encoded in the emission lines. So from that fit, we could measure star formation histories, and so we could measure an SED that is intrinsic, so that that doesn't have dust attenuation. So this is the spectrum of the attenuation-free that is derived from the star formation histories. So the intrinsic SED model is this blue spectrum, and we can measure the photometry on that blue spectrum. And then we can compare the photometry with the observed photometry. So that's why I say that the two information were disconnected. And so taking one minus the other would give us the dust law. And these were dust laws for all the galaxies in our sample. You can see there is a large variety of possible dust laws in here, some steeper, some shallower, some with the UV bump, some without. And so we compare the median dust law with other extinction laws we know from the literature, like Calcetti or a Milky Way or an SMC. And so we see that it's a little bit steeper than a Calcetti, but it's not as steep as an SMC. And this would be the best dust law for this specific sample of galaxies. But the interesting part is the scatter. So every galaxy has its own dust law. And the other work that I want to show you is the sparkler, which is an object that we found in the SMAX cluster, the very first from the very first observations from GWST. This has 3 images because it's lensed by the cluster. And in all 3 images, we see these little knots of light. And so we took the image that is the most extended and measured the photometry from these knots of light to figure out what they are. And at first sight, we thought these were knots of star formation, like active star formation in and around the galaxy. So the question was, are these things young or old? And the answer is that the majority of these things are actually old. And some are really as old as the universe when we observe it. So these are individual plots of star formation rate versus lookback time. So they're star formation histories from the individual knots of light in and around the sparkler. And we found that some of these are consistent with being globular cluster. And in other works like Claessens and Adamo also got to the same conclusion using completely different approaches, which is very nice. And so we found globular clusters in JWST images at high redshift. So I think I'm right on time. So going to conclusions. I showed you what can we learn about galaxy formation by connecting populations globally or studying the history of individual galaxies. I showed you how it's very important to think about the modeling assumptions and not use acidity fitting tools blindly. And we need to be careful because the priors, every choice is a prior, and every prior impacts the results. And so we need to account for the modeling uncertainties when comparing the results to other results or to simulations. And that with proper models and good enough data, we can actually reconstruct the staff mission histories of individual galaxies. And I showed you how we use that tool to measure dust laws and how we found globular clusters at high redshift with JWST. So I think everything can be summarized by what Julian Del Canton once said. And she said during a conference, in Romeo and Juliet, it is not just boy and girl meet, parents don't approve, boy and girl die. It is much more complex than that, and so are galaxies. So I showed you the sociological experiment, the dust laws, and the sparkles everywhere. Thank you.
Fantastic. Thanks so much. Thanks so much, Camilla. That was really great. There are lots of really interesting things here, so I'm not going to abuse my position as chair, so I'm going to open the floor to questions. So whoever you are interested, please could you raise your hand virtually, and then I can actually, and please switch on the camera. Let's see if I have any. I mean, in the meantime, I'm going to ask, my first question would be, when you have been making this comparison in the nice paper that you were basically comparing the different methods, I imagine that you were mainly using SED. So in terms of spectroscopy, if you add spectroscopic information, how much more can you constrain, or can you constrain much more than simply using SEDs? Yes,
so the story would be different with the spectroscopy. So this study applies to photometry from the UV to the near IR. With spectroscopy, I'm half hoping and half guessing that the situation would be better, that the codes would be in more agreement, but also the other half is that it is also more sensitive to the choice of the stellar population models. And I don't think it's on the archive yet, but Yasha Kushal did a very nice comparison using legacy spectra and running feeds to the legacy spectra with prospector and with bagpipes and testing different things from different tools. And so stay tuned, check it on the archive when it comes out. It has a lot of information about taking the the next big step and looking at the differences with spectroscopy and not just with photometry.
Okay, yeah. I mean, along these lines, one of the things I find amazing, I mean, you presented this very nicely. You said basically that if you just simply want to get stellar masses, no matter what you do, as long as you're doing it a bit carefully, you will be okay, which is amazing. Because another interesting thing you find is that even if you consider only SCDs and then you throw spectroscopy on top, as you're saying, you basically have an additional set of systematics. And in principle, you don't gain that much in terms of the accuracy in the derivation of stellar masses. So do you have an idea as to why stellar masses are so well behaved in general for the derivations in galaxies?
I think that that's the case when the majority of the mass is formed at early times. Even if we look at redshift 1 or redshift 2, there is very little difference between the SCDs of like 4, 5, 6, 7 giga-year-old stars. So all that matters is really the scale, the flux scale in the near IR. And I'm making it more simple than it is. But I'm saying that for that specific population of galaxies that are old and in some sense well-behaved, that's all it is. Mass is just a scaling factor. But we are seeing now with JWST and with redshift 10, redshift 11, 12 objects that the masses can be drastically different using different approaches. And that's because the simple stellar populations in the first 100 mega-year change wildly. So there we need to be very careful. It's not, what I said doesn't apply anymore.
Yeah. That's a very good point. Yeah, which is actually one of the reasons why we're having now so many differences in the results we're getting from James Webb. So
yeah,
I mean, just for a second, if you could put your James Webb scientist hat on, what is the status in terms of the calibration and all that? Because there has been already lots of interesting results, but lots of controversy. So in terms of the reduction, if you want the final quality of the results, how long should we wait until we're getting something where these variations are not so big?
I don't know. We are discovering the instruments. We are discovering even us here. It's a very complicated instrument, and we thought it would last 5 years. So we planned to make everything available right away because the community needed to use it right away, but knowing that the calibration would not be perfect. Now we know we have much more time, but we couldn't change that decision. I mean, the community would have started screaming even louder if we said, okay, now we take 2 years for commissioning because we have time, right? So we need to work together. The only thing we can do is that the people who are doing the calibration work together with the community, and we get out the best answer, and we try not to reinvent the wheel in different places on Earth, right? And we all work together to work for that perfect calibration.
Good. Yeah. Agreed. So are there any questions from the audience? Seems to be a little bit shy. So I don't see any hands raised, but so I just oh yeah, sure, please go ahead.
Yeah, sorry I didn't put my hand up. I just put my video on.
Please go ahead.
Very nice talk, Camilla. I really enjoyed that. Helps me get back in the swing of things here. I wanted to ask you about all these different fitting models, all the fitters that you engaged. Looking at that, and then I'm thinking, okay, how do I, as a researcher, fit something? And rounding up, can't really see how many there are. 12 different fitting routines, and fitting them all and taking the median seems a little,
yes,
too much, right?
Yes.
So what does one do? So that's one thing. Do you have some advice there? And the other thing is there, when you look at these different fitters, there are a lot of commonality,
yes,
which stellar population models are used and so forth. Are there specific things that are more critical than others that create the large differences between the fits? Can you talk a little bit about that?
Yes. So the first part, I completely agree. Not everybody, not for every project, one can take 12 SED fitting codes and run everything, right? So that's totally fair. I think that if one could use at least 2 or 3 at every fit, it would be ideal. The other thing, everything from this work is publicly available on GitHub. The results and the catalogs. So maybe the next person could just run the same catalog with their own code, see what they get out, see if they are in the ballpark, use this as a test bed for their other approach that was not represented in this study, and figure out if there are big biases that they need to check for, right? That's a use of this work. It's all publicly available on GitHub. The other, so yeah, I would say 1 or 2 approaches, but yes, the critical parts that we found were really the star formation histories and the dust. I think we passed the time when we all agree that we need emission lines in there, so I'm not stressing on that, but that's also very important. But having star formation histories that allow for some old population, so from some rising and declining, it's very important. And having some variety of dust laws in there is also very important. The stellar population model, if we're talking about lowish redshift things, is fine. Whatever you want to use will gonna be fine. We're seeing differences with the spectroscopy and with the very, very high redshifts. So that's another regime that will need other tuning that we don't understand yet.
Okay, thank you. That helps.
My pleasure.
Okay, any final question? So just one quick final question. When you're comparing the different attenuation laws that you're obtaining, I think it's very important that sometimes people just simply stick to a fixed attenuation law, like a Calzetti law, and that's it. And now you show, and other works as well are showing that these types of variations are there. Did you find any correlation with any of the parameters, like inclination or size or any other thing?
So Wang et al., Weich and Wang, found the correlation with inclination, so that galaxies face on had different attenuation shapes compared to galaxies edge on. So that's established, that has been seen in the past. In some sense, there is a correlation with mass as well, but everything correlates with mass. So it's hard to tell to what extent is the dust, or maybe it's the star formation rate, and so the dust is affected because of the degeneracies. So I would say inclination, definitely. Other parameters, probably, especially if they correlate with mass.
Right. So it would be very difficult to try to separate, somehow thinking along the lines of how could you separate, as you were saying, a dust composition versus the geometry of the dust. Is there any way that we could do that?
Maybe using the semiotical models that I showed at the very beginning that have dust formation and distraction included in the histories. Maybe using these, it's a completely it's a project in its own. It's a thesis in its own, exploring that. Right. So it's not something I'm planning to do at any point, but I think it would be powerful.
Indeed. So, well, if there are no other questions, thanks so much, Camilla. That was fantastic. We really enjoyed a lot this talk. And as you know, we will be putting this on the YouTube channel. So we're looking forward to your future papers on this, on the exploitation of James Webb as well. So thanks so much.
Thank you. Thank you. It's a pleasure. Thank you very much.
And thanks, everybody. You know that we will have another IAU talk in a couple of months' time. I think we have Paula Coelho slated for the next one. So stay tuned. And thanks so much. Take care.